see the screen?
Yes.
I will put it in presentation mode. Yeah. Okay, so good morning, everyone. So yesterday, I already provided some background information on the VERMEER FCM tool, and also I've also given you some information on the different models that are integrated in the VERMEER FCM tool. And so today, I will demonstrate you more in detail how the VERMEER FCM tool works by means of two case studies. So I will walk you through the case study step by step by means of slides, because in order to avoid some technical issues, I didn't want to give you a real live demonstration for the case studies, but at the end of the presentation, I will also give you a short real life demonstration. So first of all, just as a very brief reminder, so the VERMEER FCM tool consists of different modules. On one hand, there's a module with respect to migration. On the other hand, there's also a module providing you regulatory information. So this module allows you to quickly assess whether or not your compound is already included in Annex 1 for substances that are allowed to be used as starting product for plastic food contact materials. And on the other hand, there are also three modules with respect to hazards. So each of these modules corresponds to one of the migration levels as described in the notes for guidance for food contact materials. So, and as also indicated yesterday, you have to have some information about your chemical, your food contact material, and your food in order to be able to apply the VERMEER FCM tool. And as an output, you can then generate either regulatory information or migration estimate or toxicological information, or you can also have all this information together. So in fact, it's up to you to decide which blocks, which modules of the VERMEER FCM tool you would like to use, because in case you don't want to use a certain module, you can disable this block. So the case studies I will show you, they refer on one hand to a case study with food contact materials, but on the other hand, I will also demonstrate you some other possible applications of the tools by showing you a case study for cosmetic packaging. So the first case study relates to a case study with a food contact material. And this exercise has in fact been selected from a previous project of the Joint Research Center of 2010. And in fact, in this project, they wanted to provide some training on how to use migration models that were available at that time. Information about the case study we have selected. So the case study concerns a yogurt container, and in fact this yogurt container is made out of polystyrene, and it is intended for milk products. The storage conditions are at 8 degrees for more than 3 days. And in fact, when you would perform migration experiments, you would use a simulant of 50% ethanol, and the migration would be done for 10 days at 20 degrees. So the compound in which we are interested for this case study is tinuvin P. So you can see here the CAS number and the name of the compound, together with also the molecular weight and the initial concentration. So the initial concentration of this compound in the polystyrene container is 5,000 milligrams per kilogram. On the other hand, we also need some information about the food contact material. So as I indicated before, this food contact material is made out of polystyrene. You also need to know the surface, the density of the polymer. Here we have also information about the diffusion coefficient. We have the polymer specific constant, the polymer specific temperature constant, and we also know the thickness of the food contact material layer. On the other hand, we also need some information about food. So I already indicated that the container was intended to be used for milky products. The volume to be contained within the food container is 505 cubic centimeter. The diffusion coefficient is also provided over here. We also have the density, the thickness, and the partition coefficient. So in fact, we have a lot of information, so we can then start our case study. So the VERMEER FCM tool can also be downloaded from the webpage that was earlier shown in the presentation of Gianluca. And here it's important to highlight that the VERMEER FCM tool has in fact been integrated in the Merlin Expo software. So you will see if you download the VERMEER FCM tool, and that you will have the Merlin Expo software installed on your computer. And you will see that how the tool looks like. It's just very similar for other models that are integrated in Merlin Expo. What's also important to highlight is that because in VERMEER FCM, we have also integrated VEGA models. For this reason, before you start, it's also important to ensure that the VEGA is also installed on your computer. So when you open the VERMEER FCM tool, you will see that there are different tabs. And so the first two tabs, they provide you some general information. Then you have 5 tabs that relate to the modeling parameters, and I will discuss each of these tabs in detail. And then finally, you also have three tabs with respect to the reporting, so how your results will in the end be reported. So let's start first with the information tab. So if you open the VERMEER FCM tool, you will also see that there is a link to a manual. And in fact, we have compiled a kind of a very detailed manual on how to use the VERMEER FCM tool. So before you start, it can also be recommended to take a look at this manual, because there you will also see a step-by-step description on how to use the tool. So when you move then to the model tab, you will see the different modules of the VERMEER FCM tool, which I also just presented to you. And here you can just decide which modules you would like to run. In case you're not interested in a certain module, you can disable this particular building block. So then we move to the context where we will start really with our exercise, with our case study. So if you open the context tab, you will see that there is already a predefined list of compounds. There it's important to highlight that these are some of the compounds that are included in Annex 1, but not all the compounds. So it might be that you have a compound that is already included in Annex 1 that is not listed over here. These are just some examples. So if your compound is already included in the list, you can just select it and then it will appear here. And so in this part, you will in fact have the different compounds for which you will perform your analysis. Now, in our case, we are interested in tinidin P, which is not yet included in the list. So in this case, we need to push the Add button, and so then a window will appear, and here you will have the possibility to enter your information of your compound. So you can enter the name, the full name. You do not have to specify the category. This is a standard feature of Merlin Expo, but it's not applicable to our VERMEER FCM tool. And you have also then to provide here at the end the SMILES formula. And as explained before, this SMILES formula can be obtained, for example, via PubChem. However, also here, it's important to highlight again that the VERMEER FCM tool has also been developed for organic single substances, so similar as for the VERMEER CosmoLife tool. So once you have then included the information on your compound, you will be able to select it and so that it appears here in the panel with the compounds for which you will perform the analysis. And what's also of interest is that here at the right, you will see a button Information. And if you have selected your compound and you click on this information tab, regulatory information of your compound will appear. Because in this case, so the compound in which we are interested, it turns out that it is indeed included in Annex 1 and that a specific migration limit, in this case, it is a group limit, applies. And so this is also then shown over here. So once you have entered your compound, you can then select the food type in which you're interested. So I already highlighted in the beginning that the food contact material was intended to be used for yogurt. So you can select here yogurt, and you will see that then automatically also the food ethanol equivalent is already defined. However, if you're interested in a food that is not yet included in this list, you can also add a new food item, but then it's also important that you have to specify under the parameters tab the food ethanol equivalent, but I will come back to that later. So now we have in fact done everything we needed to do under the context tab. So we have provided the information on our compounds and on the food in which you are interested. So we can then move to the next tab, which has as a heading options. And here you will see that first of all, we will have to provide some information with respect to parameters characterizing the diffusion in the food contact material. Because in fact, for the diffusion coefficient and the food contact material food partition coefficient, as you might remember from the presentation yesterday, where I'd shown the complex formula behind the migration model, there are in fact two possibilities for this diffusion coefficient and this partition coefficient. Either you have your own values, you have some measured values available, then you can decide to use the measured option, because then you will insert these values, these parameter values yourself. So for our case study, we had these values available, so we have then to select the measured option. However, in case you don't have these parameters, this is not a problem. You're still able to run the migration model, but then you need to select here the calculated option. And in fact, then the diffusion coefficient will be calculated or estimated based on the Piringer's model, and the partition coefficient will then be modeled based on Huang's model, as I shown yesterday in the presentation. Another thing that you have to highlight here under the options tab is the type of polymer. As I will show you also in the real life demonstration, you have already a list of different polymers available in the tool. So if your polymer type is included, as such as is the case for polystyrene, you can just click it. On the other hand, there's also the option to do the simulation, the modeling for another type of polymer, but then you need to have some additional information. But this will be shown in the second case study. And then the last thing you have to do under the options tab is also to clarify whether your substance is included in Annex 1. And as I explained, this information can be retrieved from the context tab, because for our compound, this was indeed the case. And you can then also indicate here whether or not a specific migration limit was also included. So then we move to the next step, which relates to the time series. So here you have to specify your time and your temperature conditions. So in our case, we are interested to have an idea about the migration when we have a migration over 10 days at 20 degrees. So we fill here in 10, and here we put the temperature. But you can also play here with your data. And so you can, for example, also see what would happen if you first have conditions at 5 degrees for 5 days at 20 degrees, and then, for example, 5 days at 40 degrees. So you can specify here the conditions in which you're interested. And then we go to the next step, which is the parameters step, and there we need to fill in most of the information. So you can see that there is a long list. I will walk you also through each of these options one by one. But first of all, so I would also like to mention that for several parameters already estimates or default values are proposed by Vermeer. For example, for the diffusivity coefficient. But you still also have the possibility to change this value. So in case you have your own value and you want to use your own value, you can still change a particular value. And as also explained during the presentation yesterday, the tool does not only allow to run a deterministic modeling, but also a probabilistic modeling. And in this case, so you can specify the probability density function here. So this is again optional, so it's up to you to decide whether you want to do a deterministic or a probabilistic modeling. So now I will walk you a bit more in detail through the different steps under the parameter tab. So first of all, we need to provide some parameters describing the geometry of the system. And you will see that normally in the fields that have to be completed, they will be highlighted in red. So you will see here that, for example, for the contact area, the density of the food contact material, the thickness of the food contact material, and the volume of the food contained in your food contact material packaging, this information you need to add. And once you have entered a value, the red color will disappear. So here are the values, in fact, the information specific for our case study. So we will then have to enter these values in each of the respective fields. So then on the other hand, we also need to provide some information with respect to the parameters characterizing the diffusion in the food contact material. And here you will see that you have, in case you want to make use of the measured option for the diffusion and the partition coefficient, you will have the possibility to enter your values. So here you can also see the values that we have used for the diffusion coefficient and the partition coefficient. The diffusivity parameter of polystyrene, there will be a default value in this field. But again, if you would like to use another value, you can just easily change this value here. And the same is true for the specific contribution of PS to the diffusion activation energy. Then afterwards, we go to the section where you need to provide information on the chemical. And here you need to provide the initial concentration of the chemical as well as the molar mass. So these are for our case study listed over here. Then I briefly skip the octanol water partition coefficient. I will come back to that on the next slide. But then you also need to provide some information on the food. So the density of the food, which is highlighted here, and also the food ethanol equivalent. But in our case, this will also be automatically completed because the yogurt was already in the predefined list with food items. In case you had another food item that was not yet in the list, then you will have to specify your food ethanol equivalent in here. So I already just mentioned that I briefly skipped the octanol water partition coefficient because here you will see that after the parameter there is the VEGA tag. And when there is the VEGA tag, this means that you can model this value or this hazard, as I will show you later, with the VEGA model. So in fact, what you just have to do is you will click here on the VEGA button, which is on top. I will show you that during the real life demonstration. And then you will have this window that appears. And so you will have to do two things. So first of all, the first time you will have to select the model prediction. So you will click here and then this value will be retained. And then you will also, when you run the second one, which relates to the applicability domain index, you will have to select here the applicability domain index, and then this value will be retained. What's also important to highlight is that you will see here that there is a link to the entire report, because this can be, of course, of interest. As Emilio also explained, it's always very highly recommended to have a bit more detailed look to the prediction outcomes. And this can just be easily done by clicking on the VEGA report button. So then we come to the toxicological endpoints. So you will see here an overview of all the different endpoints for which prediction can be provided by the VEGA tool. And now you will see all of these because I had selected all the hazard modules. In case you only wanted to have the prediction for the mutagenicity and the genotoxicity, you could have disabled the hazard block 2 and 3, and then you would only see the first two models. So for mutagenicity, we have this the consensus model, and you will see again that for each endpoint, there is on one hand the model itself, which will provide you a quantitative or a qualitative value for the prediction. And on the other hand, there is also the model that provides you an indication on the applicability domain index. And this just gives you an estimate and a bit of an indication on the confidence related to a particular prediction. So again, what you need to do is you just select a certain model, and then you will click the VEGA button. And then in the case, for example, of the mutagenicity consensus model, you will see that the compound is in this case predicted as mutagenic. On the other hand, again, you can here look at the more detailed report. So you can see in this detailed report also the outcome that was obtained in each of the individual models. So this can also be interesting to have a look at. And on the other hand, it's also important to have a look at the consensus score. And we see here that this consensus score is relatively low. So we have a low reliability related to our prediction. Now here, what's important, because in fact, this consensus score already combines different applicability domain indexes, you have to enter this 0.3 value manually here in this tab. This is a bit of a bug, but in fact, it's relatively easy to overcome it by entering this score manually. And then you will see that in the end, in the outcome, the VERMEER FCM tool will in fact combine the prediction outcome together with the applicability domain index. But I will show you this example later on. So also for the NOAEL value, we can run the model. Again, you will see the outcome of the prediction and also the applicability domain index. So you will have to select each of them, so for the model prediction under the first one, and then the EDI under the second one. And then, as I explained, then the VERMEER FCM will combine these tools, these two parameters to provide you then an overall outcome in the reporting tab. So here again, you can have a look at the report. And so you will see this, that there is a predicted NOAEL value, which is in this case is about 6 milligrams per kilogram. However, here you also have to take into account that there is a low reliability associated with this NOAEL value. So again, it's always specific, especially also for this NOAEL model, important not only to look at your outcome, but also to look at the reliability that is associated with this prediction. So once you have then completed the information under all these steps, you will be able to run the simulation. In case there are still some errors or if there is some information missing, you will see a list of these errors appearing over here. And then you will have to solve these problems first before you will be able to run the simulation. With respect to the simulation, so there are some default settings, but again, in case you want to specify at which time points you want to visualize your results, this can be selected here. Also, the outputs you want to see that you can select here, and then you will only see in your output sections the different models or the different information that you have selected in here. And then when you go then to your reporting tabs, so you will see in this case, first of all, the outcome of the migration model. So for our case study, when we did this, the modeling in the conditions we have selected, after 10 days, we end up with a migration of 0.675 milligrams per kilogram food. And then you can decide whether you want to see the results either as a graph or as a table, and you can also generate PDFs. So just to give you an idea how this outcome situates to the outcomes, so the modeled migrations for other models, you can see here, so the outcome of the Merlin Expo migration model, and here you can just see the outcome of the previous models, and you see that it's very much in line. So it's very similar to the outcome of these other models. Then when we look at the toxicological endpoints that can be modeled with the VERMEER FCM tool, as I said, what will be done here in the output is that the information on the toxicological prediction will be combined with the applicability domain index. So for our compound, when we look at mutagenicity, it was predicted as mutagenic, so we have a score of 1, and then it is combined with the consensus score, which is 0.3, and in fact then we end up just with a score of 0.65. And when we look then a bit where we are, in fact, this means that tinevin P is somewhere here on the scale. So it is predicted as mutagenic, but with a rather low reliability. And in fact, also for carcinogenicity, so here you will see that in this case, we have a score of 0.5. And in fact, that means that we cannot say a lot about the carcinogenic potential of tinevin P, because in fact, it's outside the applicability domain. We also have a consensus model where the outcome of the individual carcinogenicity models is combined. But there we are also still working a bit on how to visualize and to have some extra information and guidance on how to interpret the outcome. So something also that I mentioned yesterday, so with respect to the migration model, we did the validation for the migration model for plastic food contact materials. But of course, we are still interested to do some further validation work, and specifically also to see whether the additional model that we have developed and that could be extended to non-plastic food contact materials provides very good results as well. But therefore, we need some additional experimental data. So in case you would have access to this data, or you would have some material that we would be able to use in migration experiments, of course, we'll also need then some other information about the food contact material itself. But that would also be of interest for us to help us to further validate our VERMEER FCM tool. So that's it with respect to the case study for the food contact materials. And then I just also want to demonstrate that although we have developed the VERMEER FCM tool, as it's indicated in the name, for food contact materials, there are also other possible applications. Because when we think about the packaging for cosmetics, in fact, the principle behind it, when you have to evaluate the possible risk with compounds that are present in this packaging, it's very similar to the situation for food contact materials. Because also in this case, the exposure to possible compounds in your packaging will be driven by migration. Because only when you have migration from a compound from your packaging, in this case, not a food, but a cosmetic product, there might in the end be exposure. And for this reason, we also performed a case study with a packaging for body lotion. In fact, our material was in this case an empty container made out of PVC. And so, as I said, it was intended for body lotion. And the storage conditions are in this case that the product is intended to be stored at room temperature for about 6 months. So what we wanted to do was to compare the outcome of our migration model with the outcome of migration experiments. And in fact, the migration experiments were performed in this case with a simulant of 50% ethanol to mimic this, the body lotion. And the experiments were performed for 10 days at 60 degrees. Again, we need to know, first of all, in which compound we are interested. So in this case, the compound has a really long name, but the abbreviation is luckily very short. So I will refer to it as DOTE, which has a molecular weight specified here. And so the initial concentration was indicated to vary between 0.1 and 1%. Then we also need to have some information about the packaging. So the polymer type is PVC. Here you also can see the contact area and the thickness of the packaging. And then finally, we also had some information about the product for which the packaging was intended to be used. So the volume was about 60 milliliters and the type of product was just a body lotion. And in fact, there the oily phase was estimated to be about 37%. But we know that in the migration experiments, they were done with 50% ethanol. So here as well, you will have to have the possibility to either do the modeling with 30% of ethanol, or you can do it with 50% of ethanol. So that's, of course, again, the advantage of modeling, because you do not have to do the experimental work. You can easily play with the different parameters. So here again, the steps are very similar to what I've just shown you for the yogurt case study. So first of all, you have to specify your compound. So in this case, also DOTE was not yet in the list. So you need to add this new compound. And then again, you can see whether this compound is already included in Annex 1, which indeed turned out to be the case. And then you can see here the specific migration limit that applies. And you see that again, it's a group specific group limit. And here you can see the other compounds for which the SML applies. And then you need to specify, in this case, not your food product, but your cosmetic product. So here, what we have done, because it was not yet in the list, we added the body lotion. And in fact, we, as I will show you later, we have modeled different situations. So we did, on one hand, the modeling with the body lotion, where we had a food ethanol equivalent of 37%. But then we also did one where we had just more something similar to the migration conditions, which is this 50%. So if you add here a new food or cosmetic product, then you will have to specify here under the parameters tab the food ethanol equivalence, which is in this case, not the food, but the cosmetic product ethanol equivalent. So then here we move then to the next step, which relate to the options. And so in the previous case study, we had thus measured values available for the diffusion and the partition coefficient. But here this is not the case, but luckily we can thus, although we do not have these parameters, we can just still do the modeling, but then we have to select here the calculated tab. And so this means that then in the model of Piringer and the model of Huang et al. Will be used to calculate, it's not maybe the right word, but does the diffusion and the partition coefficient. So then we move to the time series. So here I have now selected, for example, the condition where we want to do the modeling for 10 days at 60 degrees. But again, you can play with these, and you can choose to have different temperatures, different times, and so on. So then when we move to the parameter tab, so again, we need to specify here these four parameters. So we have the contact area. For the density of the food contact material, this was not yet provided to us, so we had selected this value from the polymer database. And then we also had these last two parameters with respect to the thickness of the food contact material layer and the volume of the food. Then we move to the next tab. So now we do not have to complete these measured values because we do not have them. With respect to the diffusivity parameter of this has to be PVC in our case, because now we have selected, in fact, a polymer which was not yet in the predefined lists. So this is possible to do the migration modeling with a polymer that is not yet in the predefined list. But as I explained before, then we need to have some additional information on this polymer. So in this case, we also needed to provide the diffusivity parameter ourselves, because this was not yet available. And therefore, we used this formula. Here again, different scenarios are possible. You can go for the assumption that there is 30% of plasticizer, which is quite high, and then you will end up with a value of 14.6. More realistic is probably this 6%. But here again as well, you can do the modeling for different scenarios, and then you know that when you take 30%, that you're probably in a worst case scenario compared to when you take the 6%. And so the diffusion coefficient and the partition coefficient will be calculated automatically. Yeah. You also then need to provide a polymer-specific temperature constant, and we have also based the value here on the GRC guidelines for plasticides PVC. Then we still need to provide the initial concentration. So as I'm showing you in some of the previous slides, and the initial concentration was estimated to range between 0.1 and 1%. So we have taken here also a bit as a worst case 1%, which corresponds to 10,000 milligrams per kilogram. You also see the molecular weight. We had to provide the density. Here we have taken 0.99, which is a bit in between of what was provided. And then for the food ethanol equivalent, depending on the scenario you want, you can here then have different values. And then you can see here the outcome. So it's shown here that for the conditions that were modeled, we end up with 1.87 milligrams per kilogram body lotion in our case. And again, you can either decide to present your result in a graph or in a table. So this is in fact 1.87 is what the modeling results under these conditions. So 10 days at 60 degrees with an assumed percentage of plasticizer of 30%. But you can go just to much more realistic conditions. For example, the 37% ethanol, where we have done 360 days at 20 degrees with a percentage 6% of plasticizer. You can see that the migration will be much lower and probably much more realistic. And just to give you an idea, I will also now show you the outcome of the migration experiment that were done for the compound. So there in this migration experiment, in fact, what was measured was tin. And you can see that they ended up with this concentration. Of course, you then estimate that all tin is originating from DOTE, which might not necessarily be the case. But if you would estimate that, you would come up to a concentration of 0.089 milligrams per kilogram, which is just really in line with this modeling outcome. So this is just then the demonstration of the two case studies. And maybe before I end, I will just show you now very briefly the tool in real life. So as I explained, the tool has been integrated in Merlin Expo, so you will recognize, if you have worked before with Merlin Expo, you will certainly recognize the layout. So in the information tab, you have the link to the manual. What's also interesting is that you can, here in this section, if you click the edit button, you can provide some information. For example, you can list here the different parameters that you have used to perform your case study. Then you go to the model tab, so here you can see the different building blocks of the VERMEER FCM tool. You can also display them differently. And if you click on one, you will see, yeah, it takes just some time, yeah, that you will have the possibility to disable certain of these building blocks. So as explained before, it's up to you then to decide which building blocks you would like to use for your exercise. So then you move to the context tab. So this is the list of compounds that is already included in the tool. Again, these are not all substances of Annex 1. It's just a kind of selection, some example compounds. So if it's not yet in there, you can just click the Add button and then you can specify here the information on your compound. So once you have selected your compound, so you can click on it. And if you click here, then totally at the right, the information tab, it will take some time. Yeah, but now you will see here that indeed your compound is included in Annex 1, and you will see here the specific migration limit and also the other compounds to which the specific migration limit applies because it's a group limit. So here you can then select your food item of interest. In case it is not in the list, you can just click the Add button and then a new food item will appear. You can then change the name, but the food ethanol equivalent, you will then need to specify under the parameters tab. So here you can see there's the options tab, and as I explained, you will have the possibility to either use for your diffusion and partition coefficients your own in-house values, which was the case for the yogurt case study. But if you do not have these, you can just select the calculated diffusion and or partition coefficient, and then you will still be able to perform the migration modeling. For the type of polymer, and so here you have the list with the ones that are already included, but you still, again, here you have also the possibility to run for another polymer type, so then you have to click this over here. And then here, so you can specify whether your compound is included in Annex 1, and so you can collect the information from this section. So then you go to the time series. So here you specify then the duration, so the time in which you're interested, together with the temperature. Then again to the next step. Now everything is already in white because I already completed the different fields. But as I explained, if something still needs to be completed, normally it will be in red. And so you can see here, so you can enter your value, but in case you want to do probabilistic modeling, you can specify here the probability density function. So also in this case, we are interested in polystyrene, so there will already be a value included in here. But in case you want to change it, again, you can just click on this field and then you can modify the value in whatever you want. So here, because we have selected the measured option, we need to specify here the measured diffusion coefficient and the measured partition coefficient. In the second case study, so for the cosmetic packaging, there we didn't need to complete these fields because we are using the calculated values. However, because there we were working with another type of polymer, the PVC, we would have to specify here the diffusivity parameter under a diffusivity parameter of other polymer, as well as here the specific contribution. So then here again, you need to complete the information. But what I also would like to show you is how to use the integrated VEGA models. And for example, in this case, for the octanol water partition coefficient, the value is already displayed because I have done it before. But what you can just do here is you select here the parameter, and then you click here at the button on the VEGA tab, and you see here now that the model will be running. It also takes a little bit of time. Yeah, and because here we need to specify really the prediction outcome. So first of all, we need to click here on the model prediction, and then the value will be retained. And so for the applicability domain index, I will do the same. You will see that the same window will appear. But in this case, I will have to select the applicability domain index. So you see, you have to select here your value, and then again, you have to click on OK. So in fact, for the hazard endpoints, this is very similar. So everywhere where is the VEGA tab, you can just click on VEGA, and then you will see the outcome of the VEGA model. And just also maybe for this case to show you how to access the report. So here you can see show report. So you can just click on this, and then you will see the very detailed report of the outcome in VEGA, which can be really of interest, of course. So you can either run each model individually, or you can select the different parameters for which you would like to run the VEGA model, and then click VEGA, and then everything will be run. So then finally here you also have to specify the specific migration limit because in the outcome where you have the reporting of the results, you will also be able to see there your modeled migration as a function of the specific migration limit. So once you have completed everything, you can then run the simulation. As I explained before, in case there are still some problems, these will be mentioned over here. And then you can just run simulation. And you will see here, in this case, and the outcome of the migration model. You can also see it as the table, or if you want to look at what would be the outcome for mutagenicity, of course, this outcome will not change as a function of the time, so it will always be the same. And so you can also see this over here. So I hope it was clear. So you have a bit more insights now on how to use the VERMEER FCM tool. But of course, if there are some questions, I'm certainly here to address these.
Thank you.